Okay, I'm going to go over that D to A converter happy fun quiz, and hopefully we can work through that and see how I expected you to get some of those answers pretty quick. Okay, so hopefully you can see the dots on here, and the information I gave you was that an ideal transfer function, input to output, would give you 1 volt per bit. So every time a bit change from 0, 1, 2, 3, 4, 5, 6, 7, and you never really get to 8 because it's only a 3-bit. So your binary code can go to 111, it starts at 0, 0, 0. So I got 8 different points, and my output is, in this case, goes from -1 up through 5. So you'll have these back at some point. But if you can see the dots, you can see what I'm doing here. Alright, so I asked for first the offset error, and if we look at the definition for the offset error, it's on this slide here. The offset error equals the analog output when the digital signal is 0. So we put a digital signal, an input code for 0, and we see what is the analog output. Alright, so that's straightforward, and I think most people got that just fine. If we look what happens when we have the 0 code in, which would be, typically 0, 0, 0 if it's a 3-bit code, what we get out is -1. So therefore our offset error is -1. You might also write it as 1 LSB because each bit is supposed to change by a volt, and so our offset is one entire step, one entire bit jump, one step in the negative direction. Okay, got that. The next definition we want to look at is the gain error. And in the discussion we had in class, we see the gain error is defined as the difference between the ideal gain and the actual gain after you subtract the offset error. So we're concerned here about the slope, and if I look at what's going on our the plot we have, so we start out at an input of 0 and we go to 7, so that's 1, 2, 3, 4, 5, 6, 7, 8 steps, right? From 0 through 7 is 8 different levels. And what we see is we're going from -1 up to 5. Well, we recognize the offset was -1, or 1 LSB. So we can think about shifting this whole curve up by 1 volt, which would get rid of the offset error. Okay, well, we can either draw that out. I guess I can do that. So it goes there, there, there. You could also just do this kind of mentally, see how that would look in your head. Okay, so then what we're looking for is, either way, you can take the slope from, what I'm hoping for is that as I change by 7 steps, 1, 2, 3, 4, 5, 6, 7, so I make 7 steps, and I expect, according to this, to change by 7 volts. 1 volt per bit would tell me, okay, I'd start at 0, I'd go 1, 2, 3, 4, 5, 6, 7, and that's what I expect. So I expect to get 7 steps, I expect to get 7 volts. So that would be my ideal, which would give me 1 volt per step. Okay, well, ignoring or subtracting out the offset error, what I see is, in actual, I change by 7 steps, but my voltage changes from -1 to +5, which is 6 volts, full range. So it didn't change even, or I can think of it, if I correct for the offset, I can see it's going to go from 0 up to 6, again 6 volts. So my delta voltage either way is 6 volts. My delta code is 7 steps because it gets up to here 1, 1, 1. Okay, so I'm expecting 1 volt per step ideal. Actual, what I get is 6/7 volts per step Now, I mean, you can see that most of them are actually doing 1 volt per step, but we're going to describe the whole, we want to give one number for the entire range, and typically you have a lot more than 8 levels to keep track of. So anyway, 6-7 volts per step, so my gain error is 1/7 volt per step, and you can think about this as averaging, so therefore my gain error equals 1/7 LSB, because I can, it depends if I want to talk about it in terms of voltages or I want to talk about it in terms of what my LSB, either way, because they are equivalent. If I'm trying to keep track of how off my code is, then I might want to think in terms of the least significant bits. Okay, that is gain error. The next part of this is the integral non-linearity, which is basically deviation from a straight line. So here what we're looking for, and I forget if we've got a better picture, yeah, something like that. Okay, so whether it is cyclical or has some sort of, it's just the part that isn't a line. And the easiest way to do that is to maybe grab a ruler and draw a straight line through this. Okay, so if we take either the original or the offset points, and since I'm just looking for how far off from a line this is, I'm just going to draw through the original points. That way I didn't pick up any mistakes as I shifted everything. Alright, so there would be a line. And of course this line doesn't correct for gain, doesn't correct for offset. It's just how far off from any line do we have. Whoops, okay, sorry. So just draw a line through there. And what I'm looking for is the deviation of the transfer function from that straight line. So that line through, and here I'm using the endpoint method, right? There might be a line that minimizes a little better whatever the maximum deviation is, but using the endpoints is the most straightforward way, and for the purposes of our class, what we're going to use. So I can see, that's the deviation from a line, that's the deviation, that's the deviation, that's the deviation, there's the deviation. So it looks like one of these two is going to give me the maximum deviation from that line, and that's, if you notice, that's really where my error comes in bit by bit. Okay, and then here, we're really looking for, it's on the order of 0.5 volts or about 0.5 LSB. Okay, so, filling these in, I and L, using the endpoint method, I would say it's about 1/2 LSB. And in this kind of quiz, expect you get kind of roughly in that range, and we'll be okay. All right, next definition we want to look at is differential nonlinearity. And I realize you may not be able to read the slides on the video, but go back into the ideal character or non-ideal characteristics of the DAC file, and you can see all this. Anyway, DNL is knowing that the curve should change 1 LSB every time you change the code by 1 LSB. You're looking for what is the worst deviation in a step-by-step. So now we're not thinking about the whole curve, but rather, just take individual steps, check each step across the entire range, and tell me, which one, not necessarily do I care which one, but I care what is the maximum deviation from one standard step as we move from one point to another. Okay, so that's the definition of DNL, and that's even easier, although it's getting a little crowded here, but if what I'm looking for is every one of these dots to move up one line, because my lines are a volt apart and my steps are a step apart. So from here to here there's 0 DNL. From here to here there's 0 DNL, because everything's moving up by 1, just as I expect it would. And I'm only caring about what happens between one and the next. From here to here it moves up 1 DNL. Now from here to here, this is really the only place we pick up this error, but right in here is where my step size is expected to be 1 volt as the code changes, And instead there's no change at all. You know, this is coming out at 2, and so was the previous step. So right in here, my DNL equals 1 LSB. Because I expected, as I changed the code, that this would change by 1 LSB, or 1 volts worth on the analog output. Instead, what happens is it didn't change at all. So 1 minus 0 equals 1. So the DNL is 1 LSB. You know, or you could talk about it in terms of 1 volt, but I'm going to try to keep everything in terms of 1 LSB. At the end, you know, if you keep track of all this stuff in terms of LSB, then you only have one constant you need to change at the end of everything. And we can see that the later points, you know, this moves by 1, by 1, by 1, so everything else is okay. Okay, so that was the quiz. What I was looking for then is these 4 answers, is that the offset error was more or less 1 LSB. It's in the negative direction, so you might want to keep track of that. The gain error was 1/7 LSB, and this would actually be, you know, it's actually, I suppose you would say this is a negative error also, because the gain was less than I expected it to be. The integral nonlinearity, don't necessarily have to assign a sign to that, but what we see is that it was on the order of about 1/2 LSB. The deviation from any line I can draw, at least the one through the endpoints, is 1/2 LSB. And finally, the differential nonlinearity was 1 LSB. So, pretty straightforward stuff. I think hypothetically, and expect to see this again by the time we get to the final, this is, or maybe we could give you the converse and say, you know, which of the following has these specifications, where I give you a DNL and an INL, and, you know, actually require more drawing on my part, but this kind of information probably will show up again on the final. Okay.